Hi, my name is Matthijs Broekhuizen and today we're going to look at some redox reactions. In this hood we've got two lines. One contains potassium chlorate and glucose, and the other one contains potassium chlorate and regular table sugar, which is saccharose. And what we're going to do is we're going to light the lines using some concentrated sulfuric acid. The sugar acts as a reductor, and the potassium chlorate, acts as an oxidator, which causes a violent reaction. In addition, we've also placed some salts on the mixture, and they will be alternating. There are some sodium salts, barium salts, cobalt, and copper. So we will see some color changes as the flame progresses throughout the line, and it's a cool reaction to demonstrate a redox reaction, and but it's also just fun to do. So let's watch.
The ingredients.
First we have the sodium salt, which produces a yellow flame, ounce of calcium. I believe this is the barium, which produces a very bright flame, followed by the cobalt. This is the barium. You can see a green-blue flame. And finally the copper, which produces a nice blue flame.
So that was the experiment, but how does it work? Why does the sugar burn so fast, and what causes the different flame colors? Well, first of all, the reaction we just witnessed is called a redox reaction. A redox reaction is a chemical reaction in which the oxidation state of atoms is changed. Or in other words, a redox reaction is based on the transfer of electrons. Now, the word redox is actually a portmanteau of two words, reductor and oxidator. And these are also the two types of chemicals that are needed to initiate a redox reaction. In this case, oxygen acts as an oxidator, and the reductor is sucrose, or in other words, table sugar. Now, as we've said at the start, one way to consider redox reactions is to look at them as a transfer of electrons. And in this case, the oxidator is an electron donor, so it donates or loses electrons, and the reductor actually gains the electrons. One way of easily remembering which is the electron donor or which one is the electron acceptor is by using the following English memory aid. And the memory aid is oil rig, which stands for oxidation is loss of electrons and reduction is gain of electrons. Now, if you were to take a regular scoop of table sugar and if you were to ignite it, then you would not see quite such an intense flame reaction as we have here. The sugar will probably melt and you might be able to see a tiny bit of a flame, but nothing quite as extreme as this. And that's because in a regular combustion, the sugar depends on oxygen it draws from the ambient air to fuel, or rather to oxidize the sugar. Now, in our example, we've mixed the sugar with an oxidizing agent. In our case, this was potassium chlorate. Now, potassium chlorate, when heated, will decompose and yield, in a multi-step decomposition, will eventually yield potassium chloride and oxygen. Now, this potassium chlorate is finely milled and intimately mixed with the sugar, which causes the oxygen, which is produced in the decomposition of the potassium chlorate, to be mixed throughout the mixture. It will emanate from the mixture itself, causing a very rapid burn, much faster than a regular combustion. And this is why potassium chlorate also finds use in pyrotechnics. It's a very strong oxidizer and is therefore used in certain flash mixes, which are used to produce crackers with a very loud report. Now finally, let's take a quick look at our reductor, or our fuel. Our fuel consisted of sucrose, which is the chemical name for regular table sugar. If we were to look at the equation for the oxidation of sucrose, it's basically just the regular combustion of sucrose. So the equation is exactly the same. Now the oxygen is delivered by the potassium chlorate, but that doesn't change the equation itself. Now that we've covered the redox reaction, let's take a look at the flame coloring. What produces the flame coloring in this experiment? The flame coloring is produced by different metal salts. For this experiment we chose a variety of salts containing metal ions and alternated them along the line of sugar and oxidizer. Each metal ion produces its own characteristic flame. Let's take a quick look at the salts we've used and the flame coloring it produces. First up is the sodium chloride, or the regular table salt, which produces a yellow flame, followed by calcium chloride, which produces an orange to red flame. Next is potassium chloride with a violet flame, followed by the cobalt with a bright white flame. After that, barium chloride produces a bright green and blue flame, and finally copper chloride produces an intense blue flame, and that ends the reaction. But what causes these different flame colors with different metal ions? Well, to illustrate this, let's take a look at a sodium ion. What we're seeing here is a graphic representation of a sodium ion, the core surrounded by its electrons. When this ion is introduced to the flame, some of the electrons in the ion will take up energy from the flame and enter what scientists call an excited state. This means that the energy of the flame has caused the sodium electron to go from its comfortable, stable state, which is known as the ground state, to a higher, unstable energy level, or the excited state. Because the excited state is an unstable state, the electron will eventually fall back to its ground state, and in doing so it releases the energy it has built up. This energy release comes in the form of a photon, and a higher distance between the ground state and the excited state will cause the photon to have more energy, while an excited state and a ground state that are closer together will cause a photon with less energy to emerge. Because the energy levels of the ground state and the excited state are dependent on the metal ion, every ion produces its own color. For instance, if there's a large energy difference between the ground state and the excited state, the photon that is emitted will have a high energy, which corresponds with a light color that is more towards blue and purple, for instance potassium, which produces a violet flame, and an ion which has a low difference between the energy levels of the ground state and the excited state will produce photons with a lower energy level, which corresponds with yellow or red light, like sodium or calcium.
So that was the reaction, a redox reaction with colored flames due to the metallic ions that are present in the salts that we've deposited on them. And thank you for watching.